Okay, we're continuing our discussion of calculus with parametric curves. And now we've talked about derivatives already, so now let's talk about a second derivative and what that looks like. All right, so let's look at this definition. It says if the equations x equal f of t and y equal g of t define y as a twice differentiable function of x, then at any point where, of course, dx dt is not equal to 0, again, it's the denominator, and y prime is the first derivative, dy dx, that you might have already found, then what we would say here is that the second derivative of dy dx, or the second derivative rather, d2y dx2, is going to be the derivative of the first derivative of y divided by the original derivative of x. Okay, so it may look a little confusing, but in practice I think you'll see what we're talking about. All right, so what we're going to do is we're going to take a look at a couple of examples here. All right, and the first one here says find the value of d2y dx2 at the point defined by the given value of t. So we have x equals sine t, y equals 9 sine t, and t equal pi over 3. So this problem is rather simplified. We're going to look at another example right after that's a little more involved. So this is the first derivative. All right, and let's see what it looks like. All right, we know that it's going to be dy dx. All right, and let me give me 1 second to fix this. Dy dx, okay, and it's going to be dy over dt divided by dx over dt. All right, so what does that look like? Well, it's just the derivative of y. So derivative of 9 sine t is going to be 9 cosine t divided by, and then the derivative of sine t is just going to be cosine t. Well, you should start seeing that right there crosses out. It gives you a 9, okay? So this right here represents your y prime, or your dy dx. Now, the second derivative, you probably already saw what the second derivative is, but let's go ahead and apply the formula, if you will. All right, let's apply the formula, and it says it's going to be, for d2y dx2, it's going to be dy prime over dt over dx dt. So it's the derivative of this right here, which is going to be derivative of 9, 0, divided by the original derivative of x, which was this down here, which was cosine. All right, so that is going to come back. But 0 divided by cosine is just 0. So this right here represents your second derivative that you were looking for. All right, so there's really nothing to it. All right, but we're going to look at one more example that's a little more involved. So it'll take a little bit longer to solve, but this is the gist of it. Okay, so let's take a look at another example here. Number 4 is what I'm going to call it. And I'm going to say x equals t plus the cosine of t, y equal 2 minus the sine of t, and t will equal pi over 6. So you're going to need knowledge there of the unit circle. All right. In the last one, we had a value of t, but we didn't need to plug it in because there was nowhere to plug it in. So let's see here. On this one, we're going to say the first derivative and the first derivative looks like this. Again, I'm continuing to write the formula just so you get the hang of what to do. All right. If you know what you're doing, then really no need to write it out, but it does help with the process. So you have 2 minus sine t. The derivative there is going to be cosine of t. Derivative of 2 is 0. because you have that negative sign and negative in front, you have to say negative the cosine. All right, so negative the cosine divided by derivative of x is going to be 1 plus, and it's actually 1 minus, because the derivative of cosine is a negative the sine. So 1 minus the sine of t. And this right here represents your y prime, if you will. All right, so now to find the second derivative, we recall the formula there. And that is to say that if we want d2y over dx2, all right, we're going to get dy prime over dt divided by dx dt. And I think this one should solidify the process for you here, because you are going to basically take the derivative of the y prime, which was the negative cosine t divided by 1 minus the sine t, a quotient, divided by the dx dt, which was the original derivative here, which was 1 minus the sine of t. All right, so if I'm looking at this, I should start seeing something about this. In order to take this derivative, I have to apply the quotient rule. And it's probably been a long time since you've heard about the quotient rule, but let's bring it back. All right, what do I say about the quotient rule? Well, I say low d high minus high d low over low low, all right, which is the bottom squared. All right, so I've got that in place, and I'm going to say high is negative the cosine, low is 1 minus the sine, d high is derivative of the top, or derivative of high. So derivative of cosine is negative the sine, but a negative and a negative make it a positive sign. Then d low is going to be derivative of 1, 0, derivative of sine is cosine, but it's negative, so negative cosine right there. Okay, and now I string it all together, low d high minus high d low over low low, and then once I've got all that in place, I'm going to divide that all by the 1 minus the sine t, so I can't forget that. But let's put this together, synthesize. All right, let's see, low d high, 1 minus the sine of t, d high is the sine of t, minus high, which is negative the cosine t, times a negative the cosine of t. All right, I'm already seeing some stuff play out in my head here, but let's figure this out. We're going to distribute that negative sign there, and then of course we're going to divide it by low low, which is 1 minus the sine t. All right, and 1 minus the sine t squared. I'm visualizing this already. I can already see what's going to happen here. I'm going to have a sine of t minus sine squared of t minus, and it's still going to be negative because these two here are positive, but minus a cosine squared of t divided by 1 minus the sine of t squared. All right, now I'm going to do some greatest common factor factoring, and I'm going to say sine of t minus, we pull out the negative, and that's the GCF that I'm talking about there, sine squared t plus the cosine squared t. I factored out a negative from here and from here. All right, so I did that for a reason, because I know this identity is Pythagorean. It's just 1. All right, it's just 1. So I'm going to divide that by my 1 minus sine of t squared. Now this leaves me with sine t minus 1 over 1 minus sine t quantity squared. Well, this is really nice because I can just factor out from here a negative 1, and that's what I'm going to do. And watch what I do when I do that. I'm going to end up with a positive 1 and a negative sign, and that's really neat because it will allow me to eliminate one of the factors in the denominator. Like I said, this one was going to be a little bit more involved. This is gonna leave me with a negative 1 over 1 minus sine t. And I'm gonna leave it like that, okay? 1 minus sine t. All right, now remember that we have to take this and we have to divide it by the dx dt. So let's go back over here. What was our dx dt? Well, that was this right here, the 1 minus the sine t. So it's going to be divided by another 1 minus the sine t. All right, and I'm starting to play this out in my head again, and this is exactly what I was visualizing. But remember, KFC, keep, flip, change, negative 1 over 1 minus the sine t. Always remember the KFC when dividing fractions. And it's going to be 1 over 1 minus the sine t. And what is that going to leave you with? It's going to leave you with a negative 1 over 1 minus the sine of t squared. So this right here is, of course, your second derivative. All right, that part is done, but let's go back to the question, and they want us to evaluate this at t equal pi over 6. So that's just the last and final step here, all right, is evaluate this at t equal pi over 6. So we're going to say d2y over dx2 evaluated at t equal pi over 6. All right, and now that we've done that, what does that look like for us? Well, that's a negative 1 on the top. We have a 1 minus the sine of pi over 6 quantity squared. All right, it's a negative 1 over, and sine of pi over 6 is just a 1/2 from the unit circle. So that's 1 minus 1/2 squared, which is going to be a negative 1 over 1/2 squared, which is a negative 1 over 1 over 4, which we again have to remember KFC, keep, flip, change. We get a negative 1 times 4 over 1, which is just a negative 4 as our final answer. So this right here is our second derivative evaluated at t. I keep wanting to say x. We're dealing with parametrics here. Reminder, t equal pi over 6. So there is your slope of the tangent of the tangent, I should say, I guess, right? This, of course, gives you the rate of change of the rate of change, all right, when you're thinking about it. So, again, second derivatives for parametrics. As always, I hope this video was helpful, and remember, like and subscribe.